Welcome back. We've talked about solubility. We know that even things that look like they're completely insoluble are partially soluble, a little bit's dissolving. We can calculate that now using an ice table. But let's look at another situation where we might want to worry about solubility. And it's the solubility in mixtures. And this is something commonly called the common ion effect. So let's take a beaker here, and we're going to put some copper 1 iodide at the bottom. Copper 1 iodide has a KSP of 5.0 times 10 to the minus 12th. We know that it's going to break apart here into copper 1 plus and iodide ion, which are aqueous. And if we did our ice table, right, we end up with the X and the X here. I'm shorthanding it. You should always write this out because I need to know that you're writing these out properly. Okay, but I'm shorthanding it here. And so you'd get that, your solubility is just the square root of that 5.0 times 10 to the minus 12th. And so you get that X equals 2.2 times 10 to the minus 6 molar. That's the solubility of copper iodide in water. But now what we're going to do is we're going to take and we're going to have, instead of this copper iodide sitting there at the bottom of a solution all by itself, I'm going to have it in a solution of sodium iodide. Now, sodium, we know all sodium salts are soluble, so we don't actually have sodium iodide. We have sodium ions and iodide ions. There's no more sodium iodide in there as long as we added a reasonable amount of sodium iodide. So we have the same reaction, our copper 1 iodide breaking apart into copper 1 and iodide ion, but our conditions are a little bit different. So if we put our ice table together, remember we don't care about the solid, so we just draw the line there to remind ourselves. How much copper do we have in solution to begin with? None. But now, since I've got a solution of sodium iodide that I put in, I actually do have iodide as part of my initial concentration. Because it's coming from an external source doesn't matter. Reactions don't know, well, you're the iodine from the sodium, so I don't care about you. It doesn't know, right? It's just like, hey, look, iodine, wow. And we have to take into account that iodine is there, even if it came from an external source. So that's what we're going to do. How much iodine? Let me go ahead and tell you. I'm going to say we put in 0.10 molar sodium iodide, and that's what's in that solution. And so we're just going to write 0.10 molar here. So what does that do? Right? We know we're going to make X. We know we're going to make X. This is X, and this is 0.10 plus X now. So it looks a little bit different than we did before. We still write our KSP expression is going to be the concentration of copper times the concentration of iodide, and that's going to be our KSP, which is, I just said, is 5.0 times 10 to the minus 12th. Right? And then we plug in copper is X, iodide is 0.10 plus X. Everybody's to the first because there's no stoichiometric coefficients. And so we get that as 5.0 times 10 to the minus 12th. And you might recognize that as a quadratic equation that you could certainly multiply out and solve and use the quadratic formula, things like that. But what do we know? We know we have a very, very small K value, so we don't expect this to dissolve much. And hey, this might be a place where we can use the small x assumption. Bum, 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 bum. If we look at our K value, 10 to the minus 12th, compared to our concentration, 0.1, we're doing great. We got 11 orders of magnitude. That's a very small K value compared to our concentration. So let's go ahead and do it. Small x, and we get x times 0.10. 0.10 equals 5.0 times 10 to the minus 12th. Wow, that's a whole lot easier to solve. Divide both sides by 0.1. I get that x is equal to 5.0 times 10 to the minus 13. Oh, sorry, 11. Can't do math in my head. 5.0 times 10 to the minus 11th molar. Wow. 5.0 times 10 to the minus 11th. Let's scroll back up here. Bing, bing, bing. When it was just copper iodide by itself as a solid, I got 10 to the minus 6th molar as my solubility. When I have some iodine in there, I have 10 to the minus 11th molar. That is 5 orders of magnitude. I mean, imagine your bank account being 5 orders of magnitude different, right? Oh, I've got $10 in my bank account. I now have $1 million in my bank account. You'd be like, oh, I wish I had 100, right? Wow, 5 orders of magnitude is a whole lot. So we decrease the solubility of the copper iodide by having that iodide already in solution. That's what we call the common ion effect. And it just says that solubility goes down significantly in solutions where there is already one of our ions present. It could have been the copper. If we had 0.1 molar copper nitrate, copper 1 nitrate in there, the math would have ended up exactly the same, and our solubility would have been 5.0 times 10 to the minus 11th molar. So, significantly reduced. That's our common ion effect. All right. Now your turn. What is the solubility of strontium phosphate in 0.050 molar solution of sodium phosphate? All right. Did you notice? Hey, Professor Clements always says he's going to try to trick us when he gives us these names. Strontium, Sr, 2 plus, phosphate, PO4, 3 minus. How do we have to combine that? Sr3, PO4, 2. So strontium phosphate has this somewhat complicated formula. We know it's going to dissociate into strontium 2 plus, but 3 of them, and into 2 phosphates. We can look up the KSP value for that as 1 times 10 to the minus 34th. Okay, so ICE. Oh, now we've got another thing. We've got sodium phosphate, Na3PO4. Good, there's only one phosphate here, right? So 0.05 molar sodium phosphate is going to be 0.05 molar phosphate. Good. If I was asking about the sodium concentration, it would be 3 times higher, right? So you'd have to take into account that stoichiometry. But luckily, I'm not asking about sodium. I'm asking about phosphate. Good. All right. So my phosphate concentration is 0.050 molar. So my ICE table, I don't care about my solid. I don't have any strontium, but I do have 0.050 molar of my phosphate in there. I'm going to make 3x of this. I'm going to make 2x of this. I get 3x. I get 0.050 plus 2x right there. My KSP is going to be the concentration of strontium 2 plus cubed, the concentration of phosphate 2 minus squared. And that is going to be a value of, what is it? 1 times 10 to the minus 34th. 1 times 10 to the minus 34th. Again, very small solubility, or KSP. What is that going to look like? It's going to look like 3x cubed times 0.050 plus 2x squared is equal to 1 times 10 to the minus 34th. All right. 10 to the minus 34th, it's pretty small. Let's go ahead and use that small x assumption. What do we have now? We've got 3x squared. See? See? Did you see what I did? I put a square there. No, that's a cube. It's really easy to accidentally change these things when you're, kind of trying to do it in a rush. Totally happens all the time. 0.050 squared, right? We said, hey, let's ignore that 2x equals 1 times 10 to the minus 34th. That one's pretty simple. I square my 0.05. I divide that into my 10 to the minus 34th. I cube my 3 and get 27. Divide that into my 10 to the minus 34th. So x cubed is 1 times 10 to the minus 34th over 27 times 0.050 squared. And then you solve that by putting that in, taking the cube root, and you get that x is equal to 1.1 times 10 to the minus 11th, right? And that's our solubility. Okay, let's go back up here and say, what did the question ask? It says, what is the solubility of strontium phosphate? Because great, it's that first answer. It's that answer of 1.1 times 10 to the minus 11th molar, even though if we actually calculate the concentration of strontium 2 plus, that's going to be 3x, and that's going to be 3.4 times 10 to the minus 11th molar. That's my strontium, but that's not my solubility, because solubility is always x. What's the concentration of my phosphate? It's 0.050 plus 10 to the minus 11th, which is 0.050. One thing I forgot to do on the last slide, boom, ooh, I lost a point. I forgot to check my assumption. What do we check our assumption here? We compare x to 0.050, 10 to the minus 11th compared to 0.05. Pretty sure that's less than 5%. I can say my assumption is obviously good. Right? So far beyond the chances of it being good, of it being 5%. All right, so 1.1 times 10 to the minus 11th go up. Ooh, why do I only have one significant figure? Because I only had one significant figure in my KSP value. So 1 times 10 to the minus 11th molar is the solubility. So your answer is C. Solubility in pH. So we had the common ion effect that said, hey, if I've got a common ion in my solution already, it's going to drastically reduce my solubility. So let's look at what happens in the case of a pH change. Let's start with something that's got something related to pH in it. We're going to take some lead 2 hydroxide. It's going to dissociate into lead 2 plus and 2 hydroxides. And let's say in neutral water, we could do the calculation, right? You get x and 2x, you'd square those and do all the things you're supposed to do. And you'd find that the solubility in pure water is 6.7 times 10 to the minus 6. Right, 6.7 times 10 to the minus 6 molar. But what we're going to do is we're going to put this now, instead of in neutral water, we're going to put it in a solution that's 0.050 molar sodium hydroxide. Wow, that looks like a common ion effect, doesn't it? Right? I've got sodium hydroxide that's soluble. It's going to make hydroxide ion. And so I'm going to put a 0.050 molar here. Do I put a 2 in front of that? Do I say multiply by 2? No. That 2 is a stoichiometric coefficient that comes from when lead 2 hydroxide dissociates, it makes 2 hydroxides. It doesn't say, hey, over there, some sodium hydroxide happened to dissociate. It makes twice as much, because it doesn't. Right? Sodium hydroxide is a 1-to-1 stoichiometry. It's very tempting for people to want to put a 2 and multiply that 0.05 times 2 to get 0.1, but you don't. It's coming from an external source. It's just told to you. Okay? So you don't multiply that by your stoichiometric coefficients. The stoichiometric coefficients are only for your balanced reaction. So when I do my stoichiometry next in my ice table, I don't care about that. Here I'm going to get x, but here I'm going to get 2x. That's where I do my stoichiometry. In the change part, when this reaction runs, it produces 2x. Right? Not every time I see concentration of hydroxide, I should always multiply it by 2. That's not true. Only this reaction, as it produces hydroxide, produces 2 of them. All right, so we get x, we get 0.050 plus 2x. So what do we get? We get our KSP is 1.2 times 10 to the minus 15th is x. Oops, let me write it out properly here. Is lead 2 plus hydroxide squared. And so we get x 0.050 plus 2x squared. We're going to go ahead and make that small x assumption, solve it, check our assumption, do all those things that we're supposed to do. I'm just going to give you the answer here that x is equal to 4.8 times 10 to the minus 13th molar. Right? So our solubility went from 6.7 times 10 to the minus 6 down to 4.8 times 10 to the minus 13th, 7 orders of magnitude decreasing. That is your common ion effect right there. You've got the hydroxide in the solution. It's reducing the solubility of something that has hydroxide in it, a very basic common ion effect. And if you laughed at the pun, good for you. Well, if it works in basic solution, does it work in acidic solution? Let's do this in acidic solution. Let's have 0.010 molar HCl, right, which means 0.010 molar H plus. You remember from our acids-base chapter, H plus times OH minus is 10 to the minus 14th. That means you get 1.0 times 10 to the minus 12th molar OH minus, if you remember how to do that. So let's go ahead and set this up. PbOH2 solid goes to lead 2 plus 2OH minus. And if we started to do our ice table here, we'd say we don't care about that. We got none of that. And this is 1.0 times 10 to the minus 12. This is 2x. 1.0 times 10 to the minus 12 plus 2x. X and x. And, you know, if you went and solved that, you'd be like, okay, so there's some reduction here. Not as much, right? Because I've got 10 to the minus 12. That's a very small number. I might not even be able to do the small x assumption. I might actually have to solve this one exactly. So, but there's going to be some reduction if I went ahead and solved this one. Now, I'm not going to have us solve it. I don't care about the answer to this one. But it does look like there's a common ion effect here. But what if I tell you that lead 2 hydroxide is very soluble in acidic solution? This equilibrium doesn't tell us that. Why not? Because it's ignoring the chemistry. What's the chemistry? H plus OH minus goes to water is a strong reaction. That one will run like gangbusters when it gets the chance, right? That's one of the stronger reactions, fastest reactions known to happen in solution. So that reaction will happen as soon as it can. And we said, hey, when we've got these strong acid-base reactions, like when we were doing our titrations, we have to run that strong reaction before we can run our equilibrium reaction, because otherwise the equilibrium's not there. We can't pretend there's equilibrium when there's no equilibrium. If there's somebody driving down the road at 120 miles per hour, we can't think about, let's just pretend he's stopped. No, they haven't stopped. They're going 120 miles an hour. We have to let them go 125 miles an hour or 20 miles an hour. When they stop, then we can think about when they're stopped. So what's going to happen here? I've got a bunch of H plus in solution here. Let me draw this. I've got a bunch of H plus in solution here. All this H plus, all this H plus. And as I've got a PB, a lead 2 hydroxide dissociating, boom, these guys are going to react. Boom, make some water. Fastest reaction known in solution. Whoa, super fast. So what just happened? We took this equilibrium right here, this equilibrium expression, and we removed a product. What does Le Chatelier's principle tell us what happens when we remove a product? We make more product. And so we dissociate even more. And then boom, it reacts with all that extra hydroxide or extra H plus we have in solution. We removed more product. So boom, it reacts some more. And all of a sudden you find that lead 2 hydroxide is actually soluble in acidic solution as long as you don't run out of acid. Why? Because there's a strong reaction in there, and we have to consider the strong reaction. We're not going to do this one quantitatively. We're not going to figure out exactly how much dissolves, but I'll give you a hint. Exactly as much dissolves as you have H plus in solution. You're going to run out of one or the other first. You're going to run that strong reaction to completion, then you can run an equilibrium. Okay. So, does it work for other things? Let's look at silver phosphate, right? Solid. How could we make that soluble? It's got a small KSP value. How could we actually solubilize that and make it so it could dissolve? Right? I've really got some. I need to dissolve it in water. What can I do? And there's times when we need to do that. We have these things. We need to dissolve them. We need to react them. We need to do something with them. How can we make that dissolve? What we need to do is we need to drive this reaction to the right. How are we going to drive that reaction to the right? We're going to remove a product. We can remove silver or we can remove phosphate. The one we're talking about right now is pH changes. So I'm going to put this into a solution with a bunch of H plus. I've got my phosphate in there. A little bit of it dissolves, a tiny bit because it's got a small solubility, but some does. What is phosphate going to do in the presence of H plus? Boom! Fast reaction. It's going to make HPO4 2 minus. Acid-base reaction. Boom! You've got your base here, your acid here, your conjugate acid there. It's going to react very, very quickly, eliminating a product. And Le Chatelier's principle says, hey, it's going to make more of that. So more silver phosphate is going to dissolve. Boom! It's going to react with the hydrogen. More silver phosphate is going to dissolve. Boom! It reacts with the hydrogen, until we run out of hydrogen or run out of silver phosphate. So we can significantly increase the solubility of silver phosphate by putting it into acidic solution. Why? Because this anion is a basic anion, right? It wants to take in H pluses. And so as long as I do what it wants to do, I can make it more soluble because this takes it out of the equation. It makes HPO4. HPO4 is not in this equilibrium expression. PO4 3 minus is phosphate, not hydrogen phosphate. And so it takes it out of there, drives the reaction to the right, and solubilizes the silver phosphate. So really cool things you can do. And it's general. The solubility of an ionic compound with a basic anion, right? Phosphate's a basic anion. What else is a basic anion? Hydroxide's a basic anion. What else is a basic anion? Is chloride a basic anion? No, because right, chloride is a very weak base. It's the conjugate of a strong acid. HCl loves to dissociate. It's not going to go back and try to make HCl. What other weak ones? Nitrite, carbonate, right? All those weak conjugate bases, right? Not the really super, super weak ones, right? Not the conjugates of the strong acids, but those other weak conjugate bases. If you're going to put those into acidic solution, you're going to make that significantly more soluble. And again, we're not going to quantify that, but you need to understand that, right? Sounds good. All right, lots of pictures here, but we got the idea. So, which has the highest solubility? Manganese 3 phosphate in very basic solution, copper 2 hydroxide in neutral water, or copper 2 sulfate in very acidic solution? What do you think? PO4, very basic. Am I going to get PO4 3 minus plus hydroxide? Is that going to get me anything? Right? Hydroxide wants to take an H plus. You're like, I don't got any H pluses. What? What are you going to do to me? Huh? All right, so what about copper hydroxide? Right, copper hydroxide, copper 2 hydroxide, falls apart and makes hydroxide. Is it going to react with hydroxide? Hydroxide's not going to react with hydroxide. It's not going to do much here. Sulfate in very acidic solution, are those going to react? Absolutely. Sulfate reacting with a strong acid. Hey, that's a strong reaction there. It's going to make our hydrogen sulfate ion. That removes sulfate from our equilibrium, driving the reaction to the right, and copper 2 sulfate is soluble in acidic solution. All right, so those are good qualitative things to know, and quantitatively, we're able to do the common ion effect calculations. Thanks so much for listening. Have a wonderful day.